So at equilibrium, the rates of forward and reverse reactions are equal, but the concentrations are not. How can we know what's going on with those concentrations? What can we know? Well, we can look at the equilibrium constant. It's a way of quantifying the relative amounts of reactants and products. So if we look at this reaction where A reacts with B to form C and D, and we're just using letters here, A, the lowercase ones are going to be the coefficients in the balanced chemical equation. What we define as an equilibrium constant, KEQ, is the ratio at equilibrium of the products over the reactants. So here we have the concentrations of the products multiplied by each other, divided by the concentrations of the reactants. And wherever there are coefficients, those become the exponent on that concentration. So if this was 2A, then the concentration of A would be squared. Okay? So it's the concentration of the products raised to a power equal to their stoichiometric coefficient divided by the reactant concentrations raised to their coefficients. And what we find is that that number is a constant. You can mess around with the equilibrium, but the constant will remain the same. So let's practice writing equilibrium expressions. So if we have this reaction, 2N2O5 as the reactant, and 4N2 and O2 are the products. KEQ for this reaction will be the concentration of the product, so NO2, the brackets mean that that's in moles per liter, raised to the fourth power, and O2 raised to the first power. This was an implied 1. This is also an implied 1. Divided by the reactant raised to its coefficient. You see there's a pattern there. So let's write an equilibrium expression for this one. So KEQ, it's products over reactants. So the product is HF. So we put its symbol in brackets, meaning the molar concentration. And what's the coefficient there? 2. So that's the exponent on this one. Divided by the reactants. Well, there's two reactants. There's H2 and there's F2. Their coefficients are implied 1s. We don't write the 1 because chemists like to avoid writing the 1 whenever possible. The 1 isn't written there, and so we don't write the 1 here either. You could write the 1, but what's something raised to the first power? It's just itself, right? So it's not necessary. So that's the equilibrium expression for this equation. Any questions? The value of the equilibrium constant tells us whether there's going to be more products or more reactants. So for this reaction between hydrogen and bromine, the equilibrium constant is 1.9 times 10 to the 19th. That's a heck of a big number, right? Really big. So what does that mean? Well, that's equal to the concentration of the product squared divided by the concentration of the reactants. So if this is a really, really big number, that tells me that the numerator has to be big and the denominator has to be small. So that tells me there's a lot more product at equilibrium than there are reactants. So this reaction lies far to the right. It's mostly HBr, little tiny bit of this. It's still in equilibrium though. The reaction is going in the forward and the reverse direction. When KEQ is small, it's the opposite, right? If it's small, like this 10 to the minus 31, we look at the expression, which would be similar to this. To have a small number, then The product concentration needs to be small. The reactant concentration needs to be large. So this reaction equilibrium lies far to the left. The reverse reaction is favored. So here we have the H2 and Br2 forming 2HBr. That equilibrium constant is a big number. So if you look at the composition of this mixture at equilibrium, you see that there's very little of the reactant. There's a little bit of these reactants, but it's mostly product, because the product concentration is going to be a lot higher. Looking at this one where KEQ was a small number, that tells us that the concentration of nitrogen and oxygen is going to be much larger than the concentration of the nitrogen monoxide. And we look at this picture and we see that there's very little of the nitrogen monoxide and it's mostly the reactants. This only goes a little bit, only makes a little bit of product. So if KEQ is very small, the reverse reaction is favored, the forward reaction doesn't happen very much. You've got more reactants than products. If KEQ is very large, much larger than 1, the forward reaction is favored. You've got a lot of products, very few reactants. When KEQ is approximately 1, then there's more balance between the rate of forward, the forward and the reverse reaction are going to be approximately the same. And so you're going to have significant amounts of both reactants and products. It's not necessarily equal, but they're going to be similar.